So regardless of whether we look at amino acid metabolism in the fed or the fasted state, you can appreciate from these two figures is that the amino acid pool is continually in flux and can be influenced by both dietary proteins as well as protein catabolism. Given that the major site of nitrogen disposal is the liver, a mechanism for transport of excess amino acid nitrogen from our peripheral tissues to the liver is in place. Again, both alanine and glutamine play key roles in this transport as the major non-toxic carriers. So the movement of nitrogen generally looks like this schematic with a series of transamination reactions followed by oxidative deaminations in the liver. And ultimately, this ammonia is incorporated into urea synthesis in the urea cycle. And we'll look specifically at these reactions of transamination, oxidative deamination, as well as amination of ketoacid skeletons. So we'll start with the process of transamination. So aminotransferases are a family of enzymes, and these require peroxidyl phosphate as a cofactor to help in the transfer of nitrogen from an amino acid to an alternative keto acid. What's important to note is these enzymes do not free ammonia, but will transfer the nitrogen. Two key aminotransferases to be aware of are alanine aminotransferase, or ALT, and aspartate aminotransferase, AST, as these are common and clinically relevant transferases. So, for example, if we start here with the amino acid alanine, it can undergo a transamination reaction with the keto acid alpha-ketoglutarate. Your resulting products then are alpha-ketoglutarate with the addition of a nitrogen and the keto acid of alanine. So the keto acid of alanine is pyruvate, and alpha-ketoglutarate plus an amine group is our amino acid glutamate. So we'll look more carefully at how these transaminations are useful in the movement of nitrogen. And again, this can take place with any amino acid and any keto acid. So in addition to transaminases, there are 3 additional enzymes that play essential roles in nitrogen transport. The first we'll talk about being glutamate dehydrogenase, or GDH. It's present in most tissues, and what you'll notice is different about this is it's able to both fix and free ammonia. In this example here, which largely takes place in the liver, you have glutamate coming in, interacting with NAD or NADP plus to generate our keto acid of glutamate, which is alpha-ketoglutarate, free ammonia and NADPH. The direction of the reaction will be influenced by several factors, including cellular needs, as well as the levels of NAD plus or NADP plus. Additionally, levels of free ammonia will also influence the direction of this reaction. In peripheral tissues, glutamate generated from transamination can be used to fix an additional ammonia. And this reaction is catalyzed by glutamine synthetase. So you can see here that our amino acid glutamate is fixed through a reaction that requires ATP with an ammonium to generate glutamine. And this is important because remember, glutamine is one of our primary non-toxic carriers of nitrogen, and so this is often released into the bloodstream and can circulate back to the liver. It's also important to note here that at physiological pH, the majority of ammonia, or NH3+, is present as an ammonium ion, or NH4+. The final key enzyme is glutaminase. And glutaminase is primarily active in the liver and responsible for the deamination of glutamine. So the glutamine that we just synthesized in peripheral tissues can come into the liver and be deaminated through a reaction catalyzed by glutaminase. This free ammonium can enter into the urea cycle, and the remaining glutamate compound can undergo a reaction with glutamate dehydrogenase to release our final nitrogen. So let's put these three enzymes together to see how we use them to transport nitrogen to the liver. So again, if we look at the reaction in most tissues, you have glutamate, which undergoes a reaction with our enzyme glutamine synthetase. And this can fix free ammonium to generate glutamine. From here, our glutamine can go to the liver. And within the liver, glutamine will undergo a reaction with our enzyme glutaminase. And this will free an ammonium that can then enter into the urea cycle. This leaves us with the compound glutamate. So glutamate, which I'll note as GLU here, can undergo a reaction by our enzyme glutamate dehydrogenase. This can free our remaining amino group, and this will also enter into the urea cycle. The deamination of glutamate leaves us with the keto acid alpha-ketoglutarate. So alpha-ketoglutarate at this point can enter into the TCA cycle and be used as a substrate for glucose or fatty acid synthesis depending on the fed or fasted state. Additionally, in the muscle, we also have the alanine glucose cycle, and you can see here that glutamate can undergo a transamination reaction with pyruvate to generate alanine, and alanine can then be transferred and shuttled through the bloodstream to the liver. The alanine, once in the liver, can undergo an additional transamination reaction where alanine can interact with the keto acid alpha-ketoglutarate. This leaves us with glutamate and the remaining keto acid pyruvate. Again, pyruvate can enter directly into the TCA cycle or through gluconeogenesis be used to produce glucose, which is then shuttled back to the skeletal muscle in our alanine glucose cycle. So these are the major reactions of nitrogen transport and how they're coupled together to move nitrogen from peripheral tissues into the liver for nitrogen disposal. So I'm going to finish with this question because we've focused a lot on enzymes that are active in the fed versus fasted states. And what I want you to appreciate about the urea cycle and nitrogen disposal is that this is happening in both the fed and fasted states. And that's in contrast to all the other enzymes we've talked about primarily. So we know that pyruvate kinase is a regulatory enzyme in glycolysis, and this is active only in the fed state. If we remember, in the fasted state, this is phosphorylated and inactive. That's in contrast to hormone-sensitive lipase, which is a fasted state enzyme. This enzyme is phosphorylated and active in the fasted state. And finally, glycogen synthase is a fed state enzyme, and it's dephosphorylated and active in the fed state. So the correct answer here is glutaminase. And this enzyme in the liver is going to be active in either the fed or the fasted state. If we think about this, it makes perfect sense. In the fed state, our amino acids are coming from our diet. And so in that case, they're going to the liver and will require deamination by glutaminase. In contrast, in the fasted state, our amino acids are going to the liver from protein catabolism mediated by cortisol. And in that case, once in the liver, they're deaminated and the carbons are used to produce glucose. So in both the fed and fasted states, we have nitrogen metabolism occurring. Our last piece we'll add on is the urea cycle, and we'll look specifically at how nitrogen is incorporated into urea.